Okay, going back to Michaelis-Menten, again, the X is the substrate concentration, the Y is the reaction rate V, also known as V initial. The plateau is when Vmax is reached. Km is the substrate concentration at which the reaction rate is 1/2 of the Vmax, and the graph of the Michaelis-Menten equation is going to be a curve, and then when you have the double reciprocal plot, it's just going to be a line. So the x-axis is 1 over s, the y-axis is 1 over v, the x is negative 1 over km, and the y is 1 over k max. So again, now, by using these concepts, we can actually create a more advanced view of this. So we can write that V is equal to V max concentration of S, Km plus the concentration of S for the Michaelis-Menten model, and what this model shows us is a study of how well enzymes speed up reactions. Enzymes speed up reactions, okay? So Vmax is the maximum reaction rate of the enzymes, S is the substrate concentration, Km is the Michaelis constant. Let's write that down. The Michaelis constant, substrate concentration. Again, the S is the substrate concentration. Vmax is the maximum reaction rate of the enzyme, and the rate constant. The rate constant is something that is experimentally determined for each reaction. So now let's talk a little bit more about enzyme inhibition. So moving on to enzyme inhibition, again, we had normal binding, competitive inhibition, and non-competitive inhibition. So again, during normal binding, we know that there are going to be different variants of things that can happen when it strays away from normal binding. So again, we know that during competitive inhibition, we can write that during competitive inhibition that this is when the substrate mimics the binding to the active site, and it competes for the active site. And then during competitive inhibition, that's when Km is increasing, and that's when Vmax is going to be constant. Okay, and now for moving on to non-competitive inhibition, this is when it binds to the E and the ES equally, which is like allosteric inhibitors. That's when it binds to the site other than the active site on the enzyme to disable it. And on this type of inhibition, Vmax decreases and Km is going to be constant. Okay, now for uncompetitive inhibition, which is not depicted here, but uncompetitive inhibition, well, this is when both Km and Vmax, they're going to decrease. So this is when it binds to the ES complex only. Okay. Now we can see in more detail the graphs of the enzyme inhibition plots here that we just described. So competitive, we have Vmax is unchanged and Km is going to be increased when we're looking at the Michaelis graph. And then we see that for the non-competitive, we can see that Vmax is decreased, so the curve shifts down, but the Km is unchanged. So here what we saw was the Vmax was unchanged and the Km was increased. So we see that it kind of goes like this way. And then when we see a non-competitive, this is when we see it goes this way and it also goes down this way. So this is like we can think about this is horizontally going right, and for this one we can think that it's like vertically going down, and then we can see that for this one it's going like both this and this, so it's like going down in both directions. So it's going down in the horizontal, and it's also going down